Hey, we are back. Yeah, we said we would once in a while come back with you guys and talk about the book. And this one is actually more of my father, so I'm going to let him talk. But be sure to go check out our last video. Was really quite good. And I see we're glowing live, so I'll get off of this here on my phone. And so you want to check that out. Our videos are all on our YouTube channel, which of course you can get to by going to youtube.principiamathematica2.com. You can also go to our website, which is principiamathematica2.com, and you will be able to see what's going on with our book. Some actually the table of contents, at least pretty close to what we have, and other things, including the videos that we've done. There are links to all those. So, anyways, great to have you guys on. Hello, Farouk, and I'm gonna let my dad talk today because he said he had some things he wanted to talk about. So, what do you want to talk about? I have the slides if you want to see any slides, but
Yeah, well,
why don't you give an introduction first?
let me just get started. Back years ago, I did with my gravity interest group, I did a discussion of gyroscopes and precession. I don't even remember how I explained it. I decided I didn't go back to it, but about 6 months ago, and you can put the screen up or is that
Yeah,
all right?
yeah,
Put
yeah.
the screen up for 'em. So I decided about 6 months ago to do a series on the gyroscope. This is the lead-in for slide for the one I'm going to hopefully be doing in a few days, because I finally figured out something about precession, because it's not so easy. Uh, uh, go down one slide. Okay. See, this is what I presented about 6 months ago. I said I was going to do the gyroscope and first talk about anti-gravity, which I did. And then I talked about the gyroscope. There's a situation where, although gravity is pushing down on the gyroscope, it actually moves up. And I talked about that. Then I started to go to precession, and I bombed out because I couldn't explain it. And so the third one never happened. It's a little bit of history there. Well, after we did our telethon, I did mention at the last one my next one is going to be on precession and the gyroscope. And I worked on it, and I worked on it, and I worked on it. And finally, yesterday, was it yesterday I mentioned? Yeah, it was. Yesterday morning, I think, I said to Dave, I think I have something, but I really need to talk to you about it because it isn't as clean as I would like, but it looks pretty good. I have a concern, and I'll get to that. I'd like you to go down to the one, two, three, four, five more.
Which number do you know?
The one with the dark picture.
This one?
Yeah. This is a video you can get on the internet, and I watched it, and this guy does a reasonable job of explaining this, and I captured a slide. And this is there's several of these out there, so this isn't the only one. But you notice at the top of the tire, he has a blue arrow pointing to the left, and at the bottom he has a green arrow pointing to the right. Uh, and here's what he says. If you can see me now, I don't know if
Yeah, I can. Yeah, we'll go with you.
if you can see me now. Here's what he says. He's got the tire at an angle. He's talking about it in a different part on an angle, and he says, well, when you let it loose and it's hanging on the string like that, it goes this way. So there's a force pushing here on the top to the left. That's the blue, and the green. There must be a force pushing on the other way, or he shows it here. He says there's a force there, and he uses these forces now to go through the rest of the video to explain precession. and it gets rather involved in a way to feel about it, if you're trying to understand it. But he never tells you. He tells you that there must be a force there, but he doesn't tell you what it is. Okay, that's true of the top or the bottom. He just says, well, it moves this way, so there must be a force. So even if you believe the rest of it, it sort of falls apart at this point. Now I can explain the top one. When the tire gets on an angle and you have a force of gravity pointing straight down on it, there's a component of that force pushing this way at the top. There's also one down here, and it's pushing this way. So if it's gravity that's doing that blue arrow and that green arrow at the top and bottom, they're actually going both the same way. In fact, the previous video I had that showed why the gyroscope moves up is because the pivot point's up here. This is a weaker force, this is a stronger force. The differential pushes it up. So my understanding is, so I can give you a source on the blue, but the green one still, there's nothing there. Okay, go down one slide. Where am I? Oh, that's just another example. It's the same thing with, there's two horizontal arrows there that doesn't have any explanation. It's the same thing. You can see at the top it's to the left and the bottom to the right. So it's just another example that this is how it's explained. That's the direction, no explanation of what it is. Now the next one. To me, this is kind of important. I mean, this is all about direction. If the rotor spins clockwise, clockwise, the axle precesses clockwise. And if the rotor spins counterclockwise, the axle precesses counterclockwise. To me, this is deterministic. This isn't by chance. It does it all the time. So there has to be a specific cause. Now, the rotor spins very fast. A typical is 10,000, 12,000 RPM. I mean, it's spinning like crazy. It's really fast. The axle spins too, right along with it, because they're connected. It's spinning around real fast. But here's the difference with the precession. If you ever watched the precession, it goes very slow. There's you go up 1, 2, 3, and there's that rotor is spinning really fast theoretically, and you can see that compared to 12,000 RPM, that's like 1 every 5 seconds. Maybe that's 15 revolutions per minute, something like that. So there's a big difference between, I'm just trying to make that point because that comes out later. Now all the way down to number 11. That's the drawing I made. And you guys are going to say, you expect me to follow this? It's a crazy drawing, but Dave's seen me do this many, many times. This is the rotor. The thin line going over the big circle is a rotor. On the left, up on the left, you see black arrow pointing down. That's the velocity vector. Then I got 4 velocity vectors going around, and I got force vectors. F1 gravity at the top is weak. F1 gravity lower is stronger. It's weaker at the top, stronger at the bottom. That's a key point. Now I'm going to look left and right. If you look at the forces, whether it's on the left side or the right side, it looks like it's going to have the same effect. It's the same force of gravity. It's got the same vectors, a different direction, but it's all balanced. That was one of my problems earlier. It's all balanced. I couldn't find a difference. But there is a difference left to right. If you look at the upper left quadrant, I break the force vector into two vectors. One is in line with the black vector. One is in line with the black vector. It's a force of acceleration trying to move that point faster than it's already going. That's a force of acceleration. Okay, and on the left side bottom is the same way. It's the force of acceleration is in the same direction. Now you go to the right side, it's different, and this is where the imbalance happens. The force, the black line, the vector, the velocity vector is going up, but the force vector that's in line with that black one, parallel to it, is against it, is opposing it. It's trying to slow it down, and that's the same thing up at the top. So you have an imbalance left and right. You've got an imbalance top and bottom. Top and bottom is because force of gravity is smaller at the top, stronger at the bottom. Its left and right is imbalanced. And then what the heck does that mean? You've got a rotor spinning at some velocity. One half of the left side's trying to go faster, the right side's trying to go slower.
Now this only happens in Earth gravity, right? If you were out in space where there was really, then you
No.
wouldn't have this.
No.
So in space you don't have that
You don't have
precession,
precession?
which is good because then they use it for gyroscopes to tell which direction they're going, right?
Yeah, so here's the rotor is a solid piece of metal. So what is gravity doing to the rotor if the left side is trying to accelerate and the right side is trying to compress? Well, actually the whole, if you can see me over there,
Okay. Let me know. 'Cause,
the top part is pushing down and the bottom part is pushing down. It's like the top part is under expansion and the bottom part under compression. And in order to make sense out of what I'm going to say next, you almost have to believe that gravity, as weak as gravity is, that something like that has to be going on at a very small level. So here's what I said. Here's the tricky statement, Dave. I want you to pay attention because I need some comments back. What I'm saying on the left side is that because it's being accelerated, the velocity of that side is a little bit stronger than the gravity in a normal case. Even though the gravity is the same, the effect of gravity is less on the left. And that's true top and bottom. On the right side, you've got the velocity is opposing, and so even though the velocity is going up, the force is trying to push it down, so the net acceleration is less, and the force of gravity relative to that is more. So I'm saying the force of gravity on the left is less, and the force of gravity on the right is more. Force of gravity on top is less, the force of gravity on the bottom is more, and you end up with something in the circle. If you go down one more, yes, go down one more slide, although you could expand the one you have. I redrew it. I took those force vectors and I applied them to the axle as if they were transmitted through the spokes of the rotor. Right there. The ones on well, this is hard to say because on the left-hand side, it's weak at the top, strong at the bottom. Okay, on the left side, the top one's weak, the bottom one's strong. Therefore, there must be a force in the left direction caused by those two. You go to the right, it's weak at the top, strong at the bottom. When those two are combined together, it makes a force to the right. You have two competing forces on the axle. But then you have the additional part. If you look at the difference left and right, instead, let's see what I just did. I'm losing my train of thought.
So you're trying to show the imbalance, I think.
Yeah, I'm saying those two green arrows are not the same, and I deliberately drew them differently, such that all that analysis I did ends up with the left being less and the right being more, when the two on the left combine versus the two on the right. There's another factor here I'm not getting clear. But the whole point was originally the rotor is spinning counterclockwise. If you look at the left motion and think of it as going horizontally to the left and then back and around, that force will make it go counterclockwise. That's the force you need, and it's right on the axle. The only part I have is back at the big circle, is where I'm saying the effect of gravity on the left is less, and on the right it's more. And I'm saying the gravity is less and more, even though I'm not changing the force of gravity. I'm only saying it's in relationship to the velocity changes that are happening, and somehow this compressive force at the bottom and expansive force at the top must be active somehow to make this work. I'm very uncomfortable with what I'm saying, but this is the best drawing I've come up with in terms of explaining it.
Mm-hmm.
All the mathematical explanation that I didn't show that here. Well, I did. It's in a slide. I just didn't bother with it. They talk about the angular momentum of the rotor.
Yes.
And to me, if the rotor is spinning like horizontal like this, you've got linear momentum this way and angular momentum that way. But the angular momentum vector is vertical, going straight up, and they call it a pseudo-vector. I kind of reject that just on the basis. They almost reject it themselves by calling it that.
Yeah.
And then you look at those arrows, that one guy put on, these blue and green arrows, and he says, well, it moves this way, so it has a force. You know, it may be a kind of a clever way. It's almost as difficult to understand that explanation as I just did with mine, but that green arrow's wrong. There's no justification I can see for the green arrow, except the bottom, as it falls, happens to go that way. That's not an answer.
Right, I understand what you're saying. You can have a force on the other side of it. You don't have to, just because it goes one way at the top, put force on one way, doesn't mean there's a force at the bottom doing that, right?
Yeah, in fact, when it's tilted, you've got two forces. The blue is in the right direction, the green's in the wrong direction. So that's not gravity that he's talking about. If it was, the green arrow would go the other way as well, and he doesn't have it that way. But those forces line up to give, the way I drew in my drawing, to line up to give you the possibility that the left going, the two little green arrows. And by the way, by the time, you know what the force difference between the top 2 points and the bottom two are in terms of gravity? Gravity is weak, but we're talking about the difference between those two. You know, a gyroscope is small. The F1 at top and the F1 at the bottom, that's small. Then you break it into vectors, and you go take it into the axle. Then you break that into vectors. Then you compare the two opposite ones, and the net force going this way is actually the difference between the one going left and the one going right. It's a very weak force pushing on the axle. But
Right.
remember, the precession is very slow, even though the spin of the gyroscope is tens of thousands of RPM. It's amazing.
So yeah, just for people to be reminded, the F1 force is caused by G1 particles.
Yes.
So it's like the gravity, light, magnetism, electricity particle.
You don't really need, I put it there because that's our model, and that's our model for Newtonian gravity. But when explaining the gyroscope, I'm not really.
Could the gyroscope's precession be because you can never make a perfect spinning object? It's always going to be a little off, and it just starts to get off because it's.
Well, yeah, I mean, even if it were perfect, if wind blew it over, once it tilts, it's going to precess, even if it's perfect. Even if it's perfect. But it's hard to believe that precession involves compression of the rotor. But the forces tell you that's how else can you explain how that gravitational force is acting on the rotor unless it's doing that? It's no wonder people have a hard time, and I apologize. I don't apologize for the attempt, and I don't apologize for trying to explain it, because
Are you gonna be making a video on your channel for this?
yeah, but for for all of the other viewers that watch,
Right.
I get
Is this going in the book?
gyroscopes in the book. We don't have it in the book.
Right.
We don't have about the moon spinning in the book either.
Oh yeah, yeah. I mean, there's just things that we're just looking at in general about physics.
Yeah,
So.
these are interesting points, and nothing wrong
But these
with
slides,
it,
the people will be able to see if they go to your YouTube particle.guru page, right?
Yeah, right.
Right.
I imagine in a few days I'll make the presentation, but I'm probably going to change my slides a little bit before I do that. I'm working on in the morning on one task and working on trying to squeeze this in the afternoon. And
Oh yeah, I've got my job. That's why things slowed down a little bit, but trying to catch up. Alrighty. Is there anything else, or?
no, I mean, I just wanted to, present my dilemma about, something. It's deterministic. I'll get back to that point. It's determined. It always happens, and I'm claiming there's only imbalance I see in that picture is when the force vector is in line with the velocity, and on the other side it's opposing. That creates an imbalance, which I think is the main contributor to it moving. When it's moving to the one where gravity is, I say, quote, has most effect. Oh, by the way, it would be interesting, and haven't done this obviously, to do a calculation. But you have to decide how to model this acceleration of these points around there versus the deceleration on one side versus acceleration on the other. How do you model that, put it in and then write the equations and do the calculation? But if you could do an effective model of that, you could see whether or not it's going to be offset towards that right side. Unless it's spinning the other way, then it's flipped, and yeah, it goes the other way. Interesting. But that was just yesterday morning that I actually finally applied those forces to the axle. I had been applying them all different kinds of ways, the different pictures I drew. Wasn't getting anywhere. Everything was balanced. I couldn't get it to move. This imbalance tells me there's a chance there that that's what's doing it, even if I'm not saying it right or whatever.
Right. Hacking the gyroscope. Okay, well that was very interesting. So I'm going to get back to some graphics soon. I'm trying to catch up with other things. I got my regular job going, but get started on doing and spending some time every day making some of the graphics, and we should be having updates as we go, maybe every week or so, or when my dad wants to talk about some subjects. So, alrighty.
Well, and I have a separate job I'm working on, which is taking my time from the book, which hopefully will be over this week. At least this stint will be over this week, and then I'll be back on the book on Monday. But right now it's my other job. I'm getting paid for a job, and so it gives me extra money in retirement. And I'm doing this gyroscope in the afternoon, and should be back in the book Monday.
Yep, me
And,
too. Me too. All right, and for those of you interested, we have because Farouk was by and he said I'll put that up there. He said, by the way, love your interview with Hurl. Stephen Hurl's going to be. I'm going to be interviewing him again, or no, actually, he's going to be giving a talk on. He's going to be giving a talk on Saturday at 10 a.m. Eastern Standard Time in the United States, and he's going to talk about paleogravity, which is really cool. Evidence for the gravity was a lot less in the past, so that should be fun. And then also I'll be starting some Friday night sessions with Dissident Science, so you want to check that out. But of course, again, you want to subscribe to my father's channel, youtube.particle.guru. And I think his next video is going to be on the gyroscope that he talked about in the slides he talked about.
Yes, and following that one, that's part one. Part two is about the gyroscopic effect of the Earth as it relates to the North Pole. The North Pole that sailors and people use for navigation, and as it might relate to ice ages.
Okay.
But first, to analyze, does the Earth precess? That's the question.
Right, or does it even wobble? But anyways, you can check, make sure you subscribe to his channel. He's got some really great videos he comes out with every week or a couple weeks. I also have my YouTube channel. Just got a new one out not too long ago, and I will be having Friday night sessions for people and just in general. So check it out, subscribe to that channel. And like I said, thank you for your support for our book, and stay tuned. We'll be doing these updates now and then. And have a good evening, good morning, or good afternoon, wherever you are in the world watching this. Thank you so much, everybody. Bye-bye.
Bye. Bye.